Okay, so this is another lecture or quick review about DC current. We will start by some definitions and we will do some problems. The first definition I want to start is a junction. A junction is a point where three or more than three branches, electric branches or branches from the electric circuit are connected. Okay, for example, here I have another branch where we have, another junction where we have 4 branches that are connected. There's an Kirchhoff's law that is associated with this junction. That is the sum of the current that are into the junction is equal to 0. For example, in this case, if I have I1, let's say I2, and then I3, then I can see that I1 plus I2 minus I3 is equal to 0. So the junction and the Kirchhoff's law that is associated with it is coming directly from the conservation of the electric charge. The conservation of electric charge, because the charge is not lost. Electric charge. Then there is another definition, is the loop. In a circuit, there is a loop that is, as it says, loop is a closed loop. For example, I can show this, and the closed loop has also a Kirchhoff's law that is associated with it, that is the sum of the potential difference around the loop is equal to 0. Okay, so if you start from here, let's say for point A, and you do a loop and you come back to A, the sum of all potential differences across this loop or around this loop is equal to 0. And this is coming directly from the fact that the electric force is conservative. The electric force is conservative, and one of the consequences of a conservative force is the fact that the work done to go from point A to A is equal to 0. This is a definition of a conservative force. For example, the friction force is not conservative. Okay, so let's go to another convention that we will use in the circuit. So here we will define some conventions that we will use when building a circuit or when we're calculating the current and applying Kirchhoff's law. So let's start by an EMF. An EMF, if, so this is, for example, EMF, positive and negative. If the direction of the loop is going in the positive direction, this is the loop direction. If the direction of the loop is going into from negative to positive, then the EMF will be plus E. If the direction of the loop is going in the opposite direction, from positive to negative, this is the direction of the loop, then the EMF will be minus E. Okay. Now, for the resistor, let's take, this is a resistor R. Let's assume I have a current direction in this way. So if the loop direction is going this way, this is the loop direction, then the potential difference across R will be plus IR. If the contrary, if I have same, but now I have the loop going into the same direction as the current, then the potential difference across R will be minus IR. Okay, so those are some conventions. First, the rules of Kirchhoff, which are not conventions, which are facts that are coming from Kirchhoff's law, are coming from the conservation of charge and conservation of electric force. And the convention here about the EMF battery, for example, and about the resistor. Now, let's start by the some examples on first resistors. So here we will go for resistors, the applications of resistors. And we know that when the resistors are in series, let's say I have R1, R2, R3, then the equivalent resistor here will be R equivalent, and it will be the sum, which is R1 plus R2 plus R3. And when the resistors are in parallel, okay, then, for example, if I have R1 and then R2 and R3, then the equivalent resistor here will be here, where the 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. We have already described this before. Now, let's give an example. Actually, we have already, in one of the lectures, we have explained how do you recognize two components or several components in series, and how do you recognize other components in parallel. So let's give an example. Let's consider this circuit. This is circuit where I have 2 ohms, 1 ohm, 3 ohms, and then another resistance, for example, 3 ohms, and then another resistor here, okay, with the 4 ohms, and then another resistor here, okay, that is 2 ohms, and then another resistor that has 6 ohms. And the idea, this is point A and this is point B. The idea is, what is the equivalent resistor across A, B? In other words, we want to remove all these resistors and replace it by an equivalent circuit. The first thing, we need to start from the very simple or simplifications. So we can easily see that these two resistors are in series because they are traveled by the same current. The same current is going this way, okay, or going the opposite way. So this will give, because those are in series, their equivalent resistors will be 6 ohm. Okay, so then what I can do, I can just go ahead and replace them by 6 ohm by a resistor that is 6 ohm. Okay, now we can easily see that here there is a point, a junction, and here there is a junction. So the resistor of 4 ohms and 6 ohms are parallel. So those are in parallel. How to define their equivalent resistor? So the equivalent resistor for them, well, I can call it, for example, 1. It will be 1 over 4 plus 1 over 6. So 1 over 4 plus 1 over 6, it will be 10 over, yeah, so it will be 10 over 24, which means that R1 will be equal to 12 over 5. Okay, we just simplify, and this is ohm. So Then what I can do, I can just replace this whole circuit by the new equivalent resistor, which is now 12 over 5 ohms. Now we can easily see that these two ones, this one and this one are in series, because again, if you have a current or a flow of charge here, it goes through the same. So those are in series, which means they have an equivalent resistor that I will call R2, and R2 will be just 2 ohms plus 12 over 5. Okay, which you can easily see it's equal to 22 over 5 ohms. Then I can go ahead and simplify this with another resistor that is R2, that is equal to 22 over 5 ohms. I can see that these two ones are also in parallel, which I can also name R3. So 1 over R3, because those are in parallel, it will be 1 over 1, which is 1 plus 5 over 22. So R3 will be 22 over 27. Again, I can go ahead and delete everything, and I will get the new resistor, which is 22 over 27. Of course, this is an ohm. And I can see that those three ones here, this one and this one, are in series, which means I can sum them up, and the sum will be 2 plus 6 plus 22 over 27, and the equivalent resistor will be, I can do the calculation. Okay. So the calculation would give me that the total equivalent resistor that I'm looking for, the total one, is equal to 8.81 ohm. Okay, so this is the an example on how to simplify a circuit of resistors, and also to calculate the equivalent resistor. So in the next lecture, I will go to the application of Kirchhoff's law to both the resistors and the batteries and EMF. And also in another lecture, I will also start the charging and discharging of the capacitor. Thank you for watching.